After a very long wait, it's finally here. AMD AM5. It's a new platform that comes with the new AMD Raphael desktop CPUs and Zen 4 microarchitecture. Also, it coincides with AMD's transition to DDR5 memory. In this video, we're going to have a look at all the new overclocking features and performance tuning opportunities that are available on the AM5 platform with the AMD Raphael CPU. We'll dig into the following topics. First, let's briefly review the AM5 platform, including the process, architecture, SKUs, and chipsets. Second, let's have a general look at the CPU clocking and voltage topology. Third, let's talk about CPU core overclocking. Fourth, let's talk about Infinity Fabric overclocking. Fifth, let's talk about memory controller overclocking. Sixth, we'll cover DDR5 memory overclocking. And lastly, we'll also briefly cover integrated graphics overclocking. After covering the theoretical side of AMD Raphael overclocking, we're also going to get into overclocking expectations and the practical side of AMD Raphael overclocking. First, we'll have a look at some of the Asus Crosshair X670E gene overclocking tools. Second, we'll talk about Raphael overclocking expectations for both ambient and extreme cooling. Third, we'll wrap up this video with a practical example of the AMD Raphael overclocking approach and BIOS configuration. This video is mainly targeted at people who are not yet very familiar with how to overclock AMD Ryzen CPUs and people who want to have a deeper understanding of the different overclocking technologies and tuning opportunities. However, I also hope that the people who are already familiar with AMD Ryzen can learn a thing or two from my video. All right, we have a lot to cover, so let's get started. AMD Raphael is the codename for the desktop CPUs that are part of AMD's Ryzen 7000 product lineup. They feature the Zen 4 microarchitecture and the brand new AM5 socket. It is the successor to the Zen 3 Vermeer desktop CPUs. Zen 4 is AMD's first chip produced with a modified version of TSMC's 5nm production process. TSMC's N5 node is their second generation lithography with EUV technology. Going from N7 to N5 offers several benefits, including potential increases in the operating frequency, reduced power consumption, and increased logic density. Increased logic density can be utilized in various ways. For example, making smaller and thus cheaper chips, adding more functionality like AVX512 support, or optimizing the chip layout to achieve higher frequency. I won't cover the Zen 4 microarchitecture in great detail because there will be plenty of other media and reviews taking care of that side of the story. What's important to note though is that the processor package, the physical part, is not really that much different from the Zen 3 Vermeer CPUs. Depending on the specific SKU, you'll find 2 or 3 chips on the CPU package, 1 or 2 CCDs and 1 IOD. CCD stands for Core Complex Die and is simply a chip with the Zen CCX and Infinity Fabric connections. CCX stands for Core Complex and contains up to 8 Zen 4 cores, each with their own L1 and L2 cache and a shared L3 cache. IOD stands for IO Die and includes all the IO connectivity, including the DDR5 memory controllers. Note that while the CCDs are fabricated on TSMC 5nm, the IO die is fabricated using TSMC 6nm. Key architectural differences between Zen 3 and Zen 4 include the following. Overall, architecturally, Zen 4 is more of an evolution than a revolution compared to Zen 3. It is worth noting that there are, at the very least, 2 derivative products for Zen 4. That's Zen 4 with 3D Vcache and Zen 4C. The Zen 4 with 3D Vcache is, as the name implies, a Zen 4 CCD with a layer of additional 3D Vcache on top. AMD first launched such products with Zen 3 in the form of the Ryzen 7 5800X3D for consumers and Milan X for the data center. The additional 3D Vcache greatly expands the available L3 cache on a given CCD. It is expected that Zen 4 with 3D V-Cache will be announced beginning next year. The Zen 4C is a new product designed for cloud-native compute leadership in the data center. At the moment of recording, not much is known about Zen 4C other than it having ISA parity with Zen 4, but sacrificing a little bit of L3 cache for additional CPU cores. Zen 4C is expected to launch later this year as part of the Zen 4 EPYC product line. We can speculate that the Zen 4 CCD features 2 CCXs with each 8 Zen 4 cores based on AMD's 128-core EPYC Bergamo announcement. That aligns with AMD's claim that going from TSMC N7 to N5 offers 2x density improvement. What may not be so obvious or so evident is that there's nothing stopping AMD from also introducing those Zen 4C cores on mainstream desktop. So why not have a Zen 4 8+16 or a 16+16 processor for AM5? The Ryzen 7000 desktop processor lineup again comes in 3 flavors: Ryzen 5, Ryzen 7 and Ryzen 9. So far we've only learned about the X variants, but we can safely assume that there will also be low power non-X versions sometime in the near future. The SKUs available at launch are the 16-core Ryzen 9 7950X, 12-core Ryzen 9 7900X, 8-core Ryzen 7 7700X, and 6-core Ryzen 5 7600X. I won't read through the specification of all the SKUs, but you can see the information on screen right now. The default Precision Boost 2 algorithm parameter limits can be found in this table. Totally new for AMD CPUs is that there's integrated graphics, but the integrated graphics are much more for basic display capabilities and some media functions than for gaming. It's really not intended for gaming. The integrated graphics included in Raphael CPUs is branded as AMD Radeon Graphics and carries the GFX 1036 ID. It features the RDNA 2 architecture and is part of the Navi 2 product family. The integrated graphics has 2 compute units with 128 stream processors and 1 Ray accelerator. That makes it 6 times lower specification than the Radeon RX 6400. The base clock frequency is 600 MHz and the boost frequency under load is 2200 MHz. AMD Raphael CPUs fit the AM5 LGA 1718 socket and will work on AMD 600 series motherboards. Like its predecessor, AM5 is expected to have a long lifecycle spanning multiple generations of Zen processors. With new CPUs that have new sockets come new motherboards that have new chipsets. While I won't cover the chipset features in detail, a brief overview is never a bad thing. Unlike the X570 chipset, which was designed by AMD, the 600 series chipsets are entirely outsourced to ASMedia. There are 3 configurations expected for the 600 series chipset known as Promontory 21. The high-end X670, the mid-end B650, and the low-end A620. The main difference is that the X670 features 2 daisy-chained B650 chipsets and that the A620 is a defeatured B650 chipset. There are E variants of both X670 and B650. The difference between E and non-E is that motherboards with the E designation are required to support PCIe 5.0 for both the primary PCIe and M.2 slots. In terms of performance, you may expect a potential bandwidth bottleneck on X670 when all the lanes are in use. That's because the second chipset data first passes through the PCIe 4.0 X4 lane to the primary chipset, which has its own I/O, then again passes through a PCIe 4.0 by 4 link to eventually end up at the CPU. Both the X and B series chipsets enable support for overclocking. In contrast, the A series is not expected to support any overclocking. Before we get to the overclocking, let's first have a look at the AMD Raphael platform voltage and clocking topology. The clocking of AMD Raphael CPUs is very similar to that of Zen 3 Vermeer desktop CPUs. The standard Raphael platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the ECLK PLL for the CPU cores and several SoC PLLs. The ECLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides CPU clock frequency granularity of 25 MHz. As with Vermeer, each CCX has its own PLL, with the cores within that CCX running at the same frequency. The SoC PLLs include a wide range of PLLs present on the I/O die. The ones most relevant for overclocking are F-clock for the data fabric, U-clock for the memory controller, M-clock for the system memory, and GFX clock for the integrated graphics. Unlike Zen 3, the memory controller, system memory, and data fabric run no longer at the same frequency by default. That's because DDR5 memory can run at much higher frequencies than DDR4, while the fabric clock can't. F-clock is the term used for the Infinity Fabric clock frequency. It is by default 1733 MHz, but can be set to up to 3000 MHz using the available frequency options. U-clock is the term used for the Unified Memory Controller clock frequency. It runs by default at the same frequency as the system memory, though motherboard auto rules may drop it to half the frequency if the system memory exceeds DDR5 5800. It is relatively inflexible as it can run either at the same or half the system memory frequency. It can be overclocked to 6000 MHz using the available frequency options. M-clock is the term used for the system memory clock frequency. It is by default either the same or double the memory controller frequency. It can be overclocked to DDR5 12000 using the available memory ratio options. GFX clock is the term used for the integrated graphics core clock frequency. At stock, it will go up to 2.2 GHz during a 3D load. It can currently not be overclocked. What's new on Raphael compared to Vermeer is E-clock mode. E-clock stands for external clock, and it is exactly what the term suggests, the support for an external clock generator. Support for E-clock was already available on Ryzen 2000 Pinnacle-rich CPUs, but then sort of disappeared afterward, until now. In addition to the standard internal CGPLL, Raphael supports up to 2 external clock modes. They're called E-clock 0 mode and E-clock 1 mode. In E-clock 0 mode, also referred to as synchronous mode, an external 100 MHz reference clock is used for both the CPU PLL and SoC PLLs. In other words, it's a reference clock that affects the CPU core clocks as well as the PCIe and SATA clocks. In E-clock 1 mode, also referred to as asynchronous mode, there are 2 distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. AMD suggests up to 140 MHz can be expected for the CPU core clock reference clock, but your mileage may vary. From the voltage topology perspective, there's also not that much different compared to Zen 3 Vermeer. The processor still relies on internal and external power supply to drive the voltages. There are 4 primary power supplies from the motherboard VRM to the processor: VDD-CR, VDD-CR SoC, VDD-CR miscellaneous, and VDD-IO MEMS3. The VDD-CR voltage rail provides the external power for 2 internal voltage regulators, VDD-CR CPU and VDD-CR VDDM. VDDR CPU provides the voltage for the CPU cores within the CCX. On CPUs with multiple CCXs, each CCX has its own VDDR CPU voltage rail, but the voltage will be identical. The voltage rails can work in either regular or bypass mode, but on Raphael, it is always in bypass mode. That means the CPU core voltage is always equal to the VDD-CR external voltage. VDD-CR VDDM provides the voltage for the L2, L3, and, if present, 3D V cache on a CCX. On CPUs where there are multiple CCXs, Each CCX has its own VDDCR VDDM voltage rail. This rail cannot work in bypass mode. Therefore, it is always internally regulated from the VDDCR external voltage rail. The default VDDM voltage is 0.95 volt. A quick word on bypass mode. As with previous platforms, AMD extensively uses fully digital integrated voltage regulators. The voltage regulators are ultra-high efficiency digital load dropout or DLDO. Most of the power domains, including the CPU cores, caches, fabric, and so on, have DLDOs that can be controlled individually. However, most of these DLDOs are permanently bypassed on consumer parts like Raphael. That means that regulators are disabled and the voltage regulation takes place on the motherboard via the VRM. A prime example is the voltage for the CPU cores. The DLDOs are still present on the CCDs, just like with the Vermeer Ryzen 5000 series. As an end user, unfortunately, we cannot enable them. However, we can use some specialized tools to still show you how it would work if it would be available. We can illustrate the behavior by using a single-threaded application like SuperPi32M. For stability reasons, I have to set the Fmax to 4550 MHz and the curve optimizer to +30. Then I log the system information using hardware info. Now, if we run SuperPi32M assigned to Core 1 and check the per core VIDs, we find that they're pretty much the same, around 1124 mV. That's pretty much the same as the VDDCR CPU voltage rail. And that makes sense, as disabling DLDO means we put it in bypass mode and power all CPU cores directly from the VDDCR voltage rail. When we use a specialized tool to enable DLDO and run the same test, we find that the core VIDs for each core are now totally independent. The core running SuperPi32M is running at 1100 mV, whereas the other cores are running at a different voltage between 1085 mV and 1115 mV. The VDDCR voltage rail is still at 1126 mV. If we look at the power consumption, we find that Core 1 consumes 4.27 watt in bypass mode and 4.15 watt in DLDO mode. That's a difference of 3%. When we look at the rest of the cores in the first CCD, so CCD 0, we find that the average power used in idle is 0.19 watt in bypass mode and 0.15 watt in DLDO mode. That's a difference of 21%. The cores in the second CCD, so CCD 1, idle at only 0.04 watt in bypass mode and 0.03 watt in DLDO mode. That's a difference of 16%. Unfortunately, it seems impossible to run DLDO mode when the core voltage is higher than 1.25 volt. The VDDCR voltage rail can be directly controlled via the SVI3 interface. VDDCR VDDM cannot be controlled by the end user. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for the various IP blocks, including, but not limited to, the memory controller, SMU, PSP, graphics, and so on. It is essential to know that the VDDCR SoC voltage must always be lower than VDDIO memory plus 100 mV. The default VDDCR SoC voltage is 1.05 volt. VDDCR GFX provides the voltage for the GPU cores on the I/O die. The voltage rails can work in either regular mode or bypass mode. In regular mode, the voltage is managed by the integrated voltage regulator and derived from the VDDCR SoC voltage rail. When the integrated voltage regulator is in bypass mode, the voltage is equal to the VDDCR SoC voltage rail. The VDDCR SoC voltage rail can directly be controlled via the SVI3 interface. The VDDCR miscellaneous voltage rail provides the external power for the internally regulated VDDG voltage rail. VDDG is the voltage supply for the Infinity Fabric data path. There are a total of 4 independently configurable VDDG voltages. Each represents a specific GMI link connection. When overclocking your DDR5 memory, you may need to manually increase the VDDG voltage as it does not automatically adjust when changing the VDDCR miscellaneous voltage. The VDD-CR miscellaneous voltage rail can be directly controlled via the SVI3 interface. In contrast, the VDD-G voltages can only be configured using the CPU registers. The default VDD-CR miscellaneous voltage is 1.1 volt, and the default VDD-G voltage is 0.85 volt. The VDD-IO MEM-S3 voltage rail provides the external power for the VDD-P DDR internal voltage regulator. VDD-P is the voltage for the DRAM PHY. As a rule, VDD-IO MEM should always be higher than VDD-P DDR plus 100 mV. When overclocking, you may need to manually increase the VDD-P voltage, as it does not automatically adjust when changing the VDD-IO MEM voltage. The default VDD-IO MEM voltage is 1.1 volt. The default VDD-P voltage is 0.8 volt. AM5 Raphael desktop CPUs support the brand new SVI3 interface. SVI stands for Serial Vid Interface, and it's an AMD designed technology or interface that facilitates communication between the CPU and the voltage regulators. AMD introduced the first generation SVI to NDA partners in January 2006 as the successor to its PVI technology. It was introduced to the market with socket AM2 Plus processors about 1 year later. The main advantage of SVI is that it provides an I2C compliant interface between the CPU and the VR controller. I2C requires only 3 connections for data, clock, and ground. This removes the need for increasing the number of parallel connections between the voltage regulator and CPU to support additional features and voltage range. The second generation SVI was available to NDA partners in February 2010 and provides a range of features including greater granularity in voltage selection, faster data rate, and telemetry functions. It was introduced to the market with socket FM2 Trinity processors in 2012. The third generation SVI was available to NDA partners in November 2018 and was first implemented on the 2022 Ryzen 6000 Rembrandt mobile APUs and is now also available on AM5 Raphael. The Serial VID interface version 3 is designed to provide a scalable single master multi-slave communication bus for power management on AMD platforms. SVI3 represents a significant deviation from SVI2 and all previous AMD power management interfaces. SVI3 is not designed to be backwards compatible with SVI2, so some SVI3 devices may not be able to communicate over the SVI2 bus. However, advanced devices may support SVI2 as well. Precision Boost 2 is a performance optimizing technology that's been present on all AMD CPUs since the 2018 Ryzen 2000 processors. It enhances performance by dynamically increasing the processor frequency at runtime. Precision Boost 2 behavior depends on several factors, including temperature, power consumption, current draw, and the number of active cores. We don't have up-to-date information on how exactly the Precision Boost 2 algorithm works with Zen 4 Ryzen 7000 processors. However, AMD detailed how Precision Boost works on the first generation Zen in a 2018 paper titled Zeppelin, an SoC for multi-chip architectures. We can assume that the technology still essentially works in the same way. The Precision Boost magic is performed by the SMUs. SMU stands for System Management Unit, and every chip on your AMD Raphael CPU has an SMU on board. That means on Raphael CPUs with 2 CCDs and 1 IOD, you have a total of 3 SMUs. One of these SMUs will work as master SMU, while the others work as slave SMUs. Typically, the SMU in the IO die would be the master SMU. All SMUs are connected using a low bandwidth control bus called SCF or Scalable Control Fabric. The SMU has a range of capabilities, including, most importantly, the ability to manage the CPU performance within the infrastructure constraints. The infrastructure restricts the maximum operating limits on various metrics, including power draw, temperature, and voltage. We don't have a comprehensive confirmed list of the metrics, though some are exposed to the end user. On Raphael, the exposed infrastructure limits include the following. We'll have a closer look at each of these in a minute. The primary function of the slave SMUs is to capture the measurement data related to the infrastructure limits, then prepare that data to be sent to the master SMU. The master SMU's primary function is to analyze the package-wide measurement data and determine the actions needed for performance management. Each infrastructure limit has its own algorithm and is managed independently by the master SMU to determine the infrastructure limited frequency. The process for each algorithm is as follows. First, receive the data from the slave SMUs, then aggregate the data into a single evaluation, with the output being the maximum frequency limit for a given infrastructure algorithm, then input the results to a PID controller, which smoothens out the responses over a longer period and avoids spikes or quick changes. Lastly, the changing output of the PID controller is the maximum frequency allowed by a specific infrastructure limit at a given time. This process is repeated approximately every 1 millisecond for each algorithm. The firmware then selects the most constraining limit as the global frequency limit. Then either of two things can happen. The current frequency exceeds the limit, or it doesn't. If it does, the frequency is reduced, and if it doesn't, there's frequency headroom and the frequency will increase. Either way, the master SMU passes the frequency change request to the slave, and each slave applies the frequency changes to the CPU cores of the local die. The frequency changes are coordinated with the global voltage plane by the master SMU. If the frequency increases, the master sends a VID voltage command to the external voltage regulator before sending frequency increase commands to the slave SMUs. If the frequency decreases, the master first sends the frequency change request to the slaves, then it waits for the frequency change to be acknowledged, and lastly it sends the VID voltage command to the voltage regulator. The slave SMUs can make independent decisions based on local conditions. So it can apply lower frequencies than the frequency requested by the master SMU if the on-die conditions require so. Now let's have a closer look at the precision boost infrastructure limiters exposed to the end user. Note that all of these limiters are present on Ryzen 7000 CPUs, although not all of them may be defined or active because some limiters are not relevant for desktop CPUs. Sustained power limit, or SPL, is the processor power that can be sustained indefinitely by the power supply and thermal solution. It is also known as the TDP. Package power tracking, or PPT, is the total power the processor can draw from the socket before the boost levels off. Typically, the limiting factor is your CPU thermal solution. In technical documentation, you'll find that PPT is actually a combination of 3 power-related options: PPT APU, fast package power tracking, and slow package power tracking. Depending on your platform, some of these parameters may not be used. For desktop Raphael, fast PPT is the parameter we override when configuring PPT. Electrical design current, or EDC, represents the maximum peak current the voltage rail can demand under transient conditions for a short, thermally insignificant time. Independent EDC tuning is available for both the VDDCR and VDDCR SoC voltage rails. Typically, the limiting factor is the choice of VRM components and their maximum rated specification. Thermal design current, or TDC, represents the maximum sustained current the voltage regulator can support. Independent TDC tuning is available for both the VDDCR and VDDCR SoC voltage rails. Typically, the limiting factor is the choice of VRM thermal solution and the VRM components. Thermal, or THM, represents the thermal block inside the SMU that contains all temperature sensors, control, and reporting features. The THM limit is the maximum allowed processor operating temperature and is commonly known as TJ max. High temperature Fmax, or HTF max, represents the maximum frequency allowed at high operating temperature. This limiter is SKU specific and may or may not be present. For example, on the 7600X, the HTF max limiter starts at 5450 MHz at 70 degrees Celsius. The frequency reduces linearly until it reaches 5150 MHz at 95 degrees Celsius. However, On the 7900X, this limiter does not appear to be present. Processor hot or proc hot is a signal within the motherboard design that tells the processor the other system elements are overheating and allows the processor to throttle performance. Skin Temperature Aware Power Management, or STAPM, represents the maximum power the processor can use within the thermal budget of the whole system. It is similar to the package power tracking, but also considers the system thermal capacitance headroom. It is primarily relevant for notebooks and not so much for desktop. C-State Boost is a specific boost limiter present on early Raphael engineering samples. Effectively, C-State Boost limits the maximum frequency when a certain number of active cores is exceeded. For the 16-core 7950X, the C-State Boost limit would force the CPU to run at 5.2 GHz when more than 4 cores are active. This precision boost limiter is not active on retail processors. Failures in time, or FIT, is a standard reliability engineering metric used in the semiconductor industry. It represents the rate at which a component fails over its lifecycle. For semiconductors, operating voltage and temperature are the most relevant factors for failure. AMD's real-time reliability monitoring technology incorporates two critical limiters to long-term reliability in high-performance microprocessors: time-dependent dielectric breakdown, TDDP, and electromigration, or EM. The FIT rate is calculated in a 1 millisecond interval using the following formula. The subscripted variables are curve fit based on the foundry process reliability models. So for Raphael, that's based on the reliability models provided by TSMC. Voltage identification, or VID, is a way for the CPU and voltage controller to communicate voltage requests. The VID limit is the maximum allowed voltage for the processor. The VID limit is factory fused and cannot be changed by the end user anymore. Fused maximum frequency, or Fmax, is the maximum allowed processor frequency. This value is fused from the factory and is obviously a core part of the CPU specification. So far, I've talked about the Precision Boost 2 limits and everything that is constraining the maximum frequency. But we haven't talked yet about how this maximum frequency is actually calculated and estimated. Since the 2015 Carrizo APU, AMD has used Adaptive Voltage Frequency Scaling, or AVFS in short. This technology relies on critical path accumulators for estimating the maximum stable frequency of circuits inside the CPU. If it sounds complicated, that's because it is. However, I'll try to explain it as simply as possible. The long story short is that AMD adds replica paths to the circuit that serve no other purpose than to assess whether the circuit is stable or not. The AVFS technology extracts a Gaussian distribution statistical model from the replicate paths. It infers the stability of the real paths using sampling statistics. This statistical data is used by the SMU to create a voltage frequency temperature, or VFT, table. The VFT table is a part-specific lookup table with information on the optimal voltage for any combination of frequency and voltage. The higher the frequency and temperature, the higher the required voltage to ensure stability. While extracting this VFT table from the CPU cores is not possible, I can still somewhat illustrate how it works. In this case, I assigned a workload to a specific Zen 4 core. I tracked the VID request across the different frequencies and temperatures. We can make 3 observations from the table. First, obviously, for higher frequencies, the CPU needs higher voltages. 2, for a given frequency, the CPU requests higher voltages as the temperature increases. For example, 4.6 GHz below 40 degrees Celsius uses 1.02 volt, and above 90 degrees Celsius, it uses 1.068 volt. Similarly, 5 GHz below 40 degrees Celsius uses 1.145 volt, and above 90 degrees Celsius uses 1.244 volt. Third, you can see that the CPU won't boost to the highest frequencies at high temperatures. For example, over 80 degrees Celsius, the highest frequency is 5300 MHz at 1.368 volt. This is the result of the precision boost frequency limiters we discussed before. Back in 2015, this VFD table consisted of 10 rows and 8 columns, so 80 distinct data points. It's not entirely clear if that's still the case with the Zen 4 Ryzen 7000. Furthermore, each core inside your CPU has its own VFD table, so for a 16-core Ryzen 9 7950X, you'd have 80 times 16 or 1280 data points. Note that this VFD table is a factory fused table created during manufacturing. And now I hear you asking, what if my power supply is terrible? Great question. AMD uses automated test equipment, ATE, to fuse the VFD table onto a CPU. This test equipment typically provides a more robust, less noisy power supply than a consumer power supply. To compensate for this, AMD uses a tester to platform, T2P, voltage offset. It is often a conservative over-margined value. AMD employs a boot time calibration (BTC) process to fine-tune the voltage offset. Essentially, during the boot process, the CPU can check the quality of the power delivery. Based on the quality, it then offsets the factory-fused VFD table. If you have a great power supply, the offset will be smaller. If you have a terrible power supply, then the offset will be greater. The practical implication of boot time calibration adjusting the voltage offset is that you can have different voltages for the same CPU depending on the power supply network. The power supply network includes the power supply, the motherboard VRM, and other electrical components between the wall socket and your CPU core. A great power supply network would result in a smaller boot time calibration voltage offset, thus yielding a lower operating temperature. Conversely, a poor power supply network would result in a larger boot time calibration voltage offset, thus causing higher operating temperatures. I don't have time to test this in the real world, but I'm sure there's some tech media out there that is doing this kind of testing. Despite having these really advanced technologies like AVFS or the part-specific voltage frequency table or the tester to platform voltage offset and boot time calibration, AMD can still not exactly predict what will happen in the real world. Sometimes the transient conditions are so rough that the jump from idle to load or load to idle causes the voltage to drop too much, and that would result in a system crash. Fortunately, AMD CPUs also have voltage adaptive operation technology, more commonly known as clock stretching. The technology consists of two circuits. One circuit serves as a configurable droop detector, and the second circuit functions as a configurable digital frequency synthesizer. For example, we could configure that if a voltage droop of 2.5% or more is detected, the clock period is increased by 5%. The effect is simple. If a voltage droop is detected, the effective clock frequency is lowered to ensure continuous operation instead of a system crash. In the real world, this technology is incredibly relevant when overclocking because it may cause effective performance at a given frequency to be lower than expected. Fortunately, we can quickly check if our system is clock stretching using tools like Hardware Info. The practical implementation of clock stretching is that the effective clock frequency will be lower than the configured core frequency. It is essential to distinguish between these two terms. The core frequency results from the reference clock multiplied by the CPU ratio configured by your motherboard and processor. It is a snapshot of the configured frequency at a specific moment in time. The effective clock frequency is the total clock cycles between two moments. It measures the actual performance of your processor within a period. You can check this value with specific tools like Hardware Info. As illustrated in this example, the effective clock between two moments may be lower than the core frequency snapshots taken at those specific two moments in time. This can be due to changes in environment like workload, power saving features when a core is idle, or clock stretching. The best way to check if clock stretching is happening is by comparing the core frequency with the effective clock. Suppose the effective clock is significantly lower than the configured core frequency when the system is under load. In that case, clock stretching is likely happening on your system. If you're increasing CPU frequency but seeing stagnation or even a reduction in benchmark performance, clock stretching might be the reason. Overclocking the Zen 4 Raphael CPU cores is really not that different from overclocking the Zen 3 Vermeer cores. So anyone who's already familiar with Zen 3 will be very quickly also familiar with overclocking Zen 4. For those who are not familiar yet, let me give you a quick rundown. There are two main avenues to AMD Ryzen CPU core overclocking: Precision Boost Overdrive and OC mode. Precision Boost Overdrive allows you to tune some of the parameters governing the Precision Boost CPU frequency boosting algorithm. By adjusting the parameters, you can achieve better performance. OC mode disables the automatic frequency boosting technology and gives you manual control over some frequency and voltage parameters. Precision Boost Overdrive 2, or AMD PBO2, is AMD's Precision Boost Overclockers toolkit. It allows us to manually tune some of the parameters that are governing the Precision Boost algorithm. Essentially, it allows us to configure the Precision Boost algorithm such that we have higher boost for longer periods of time and therefore substantially improve the system performance. A crucial advantage of Precision Boost Overdrive is that it retains all the intelligent frequency boosting mechanisms present in Precision Boost. That means you get both the high frequency single core and medium frequency all core boost. That sets it apart from manual overclocking, as you'll see later in this video. The Precision Boost Overdrive 2 toolkit for Zen 4 is identical to the toolkit of Zen 3. So anyone who's already familiar with PBO2 can skip this part of the video. If you're not, I'll gladly reiterate how everything fits together. There are a total of 7 tools available to tune the Precision Boost 2 algorithm: 4 platform configuration tools and 3 CPU configuration tools. Package power tracking, or PPT, is the total power the processor can draw from the socket before the boost levels off. Typically, the limiting factor is your CPU thermal solution. Electrical design current, or EDC, represents the maximum peak current the voltage rail can demand under transient conditions for a short, thermally insignificant time. Typically, the limiting factor is the choice of VRM components and their maximum rated specification. Thermal design current, or TDC, represents the maximum sustained current the voltage regulator can support. Typically, the limiting factor is the choice of VRM thermal solution and the VRM components. Platform thermal throttle allows the user to decrease the maximum allowed processor temperature. The configurable values range from 0 to the product-specific TJ max, which typically is 95 degrees Celsius. Lowering the thermal throttling point is generally not recommended, as it will negatively impact your performance. However, it can be helpful if you want to run a temperature as low as possible. Scaler is a tool that allows the user to override the warranted silicon stress level, or FIT, to achieve higher frequency. You can adjust the maximum allowed FIT levels to 10 times higher than the factory fuse limit. While the tool offers precise granularity, typically you'll find the available options to range between 1x and 10x in steps of 1 multiple. The effect of increasing scaler is that the Precision Boost algorithm should aggressively pursue higher voltages, as it is less concerned with CPU lifespan. Boost Clock Override, or Fmax Override, allows the user to override the arbitrary clock frequency limit between -1000 MHz and +200 MHz in steps of 25 MHz. It is available for both the CPU core clock and, if present, the graphics core clock. It is important to note that the override only adjusts the upper ceiling of the frequency and does not act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. On some motherboards, you may see Fmax override options higher than +200 MHz. While it may be possible to write these values to the processor registers, they won't actually get applied. Curve Optimizer is a tool that allows the user to adjust the voltage margin of each individual CPU core. It does this by offsetting the voltage of the CPU core VFT table. While you don't have exact control over the voltage of each frequency temperature point, Curve Optimizer allows you to effectively undervolt your CPU. Curve Optimizer allows end users to adjust the factory-fused VFT, or voltage frequency temperature curve, for each CPU core separately. The VFD curve is a unique curve for each core inside your CPU that defines the required voltage for a given frequency at a given temperature. Higher frequencies or higher operating temperatures require higher voltage. Curve Optimizer adjusts the VFD curve by offsetting the voltages of the VFD curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. You can offset the entire curve by up to 30 steps in a positive direction and up to 300 steps in a negative direction. Each step represents about 5 millivolts. It may seem odd that the negative curve side is expanded to 300 steps, but I'll get back to that in a minute. The traditional approach to AMD Ryzen CPU overclocking is by configuring a negative curve optimizer setting. Two things happen when you do this. First, you effectively tell the CPU that it needs less voltage for a given frequency, and as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the precision boost algorithm to target higher voltages and frequencies. Now to get back to that -300 curve optimizer. The public tools and public BIOSes currently only support up to -30 steps, so it's a little bit difficult to illustrate how it works. But using non-public tools, I was able to gather some data that hopefully helps you understand what's going on. The approach is straightforward. I record the actual voltage and effective clock frequency during a workload as I adjust the curve optimizer setting. I do this for 3 scenarios where I vary the voltage offset from the CPU vCore voltage regulator. As a quick reminder, the CPU will issue the voltage request to the voltage regulator with a VID request. The voltage regulator then adjusts the voltage output according to this request. When we use a negative curve offset, the VID request from the CPU is lower, and thus the voltage output from the voltage regulator is lower. We can also configure the voltage controller to add a positive offset to the VID request. Then the output voltage will be the CPU VID plus any offset from the controller. The 3 scenarios are 0 mV offset, plus 50 mV offset, and plus 100 mV offset. First, look at the chart mapping the curve optimizer setting and the actual voltage. As you can see, adding a voltage offset to the voltage controller adjusts the impact of the negative curve optimizer on the effective voltage. For example, at -40 curve optimizer, the actual voltage is 1.22 volt with 0 mV offset, 1.257 volt with 50 mV offset, and 1.288 volt with plus 100 mV offset. Also, 1.22 volt is achieved with a curve optimizer setting of -40 with no offset, -52 with 50 mV offset, and -64 with 100 mV offset. Second, let's look at the chart mapping the voltage frequency curve. Here we can see the impact of curve optimizer and voltage offsets on the operating frequency. The curve is homogeneous, indicating that the precision boost algorithm always tries to maximize the frequency for a given operating voltage, regardless the curve optimizer or voltage offset. We can see that at 1.23 volt, the frequency is 5290 MHz with a -29 curve optimizer and no voltage offset, 5298 MHz with a -50 curve optimizer and plus 50 mV offset, and 5306 MHz with a -62 curve optimizer and plus 100 mV offset. Further experimentation showed me that -72 works if I use a offset of 150 mV, and if I use an offset of 750 mV, I could even go all the way up to, or down to, however you think about curve optimizer, down to -300. However, beyond -300, there was no more effect on the voltage or frequency. In the Asus ROG BIOS, you can access the Precision Boost Overdrive settings via the Extreme Tweaker Precision Boost Overdrive submenu. Alternatively, you can also use the Precision Boost Overdrive submenu settings in the AMD Overclocking menu. In addition to Precision Boost Overdrive 2, AMD also allows overclockers to take direct control over some of the voltages and the frequencies of their CPU. This is unofficially called OC mode, and when you enable OC mode, all performance boosting and power saving technologies are disabled. One could question the use case for manually overclocking an AMD Ryzen CPU. Just like with all past Ryzen processors, the major downside of manually overclocking is that you lose the benefits of precision boost technology yielding high frequency and low threaded benchmark applications. So, whereas a 7950X can boost up to 5700 MHz with precision boost, it will be limited to your set fixed frequency when manually overclocking. However, manual overclocking is not all negative, and it even has some benefits. First, automatic overclocking and frequency boosting technologies leave a little margin on the table. We can exploit this margin and fine-tune for application and system-specific stability when manually overclocking. Second, on AMD Ryzen CPUs, you can set the frequency for each CCX separately. So we can exploit the fact that some CCXs may overclock better than others. This is particularly relevant for the Ryzen 9 7950X and 7900X. Thirdly, by setting a fixed voltage, we avoid the CPU dynamically and rapidly updating its VID requests to the VRM controller. This alleviates stress on the VRM and typically yields lower temperatures. The maximum stable frequency will depend on your desired level of stability and the choice of stress test tool. In the Asus ROG BIOS, you can configure a manual CPU overclock via the Extreme Tweaker CPU core ratio per CCX submenu. Alternatively, you can manually adjust the CPU core frequency in the AMD Overclocking manual CPU overclocking submenu. It is worth remembering that AMD Raphael supports 3 clock generator modes: internal clock generator, ECLK synchronous mode, and ECLK asynchronous mode. ECLK asynchronous mode is particularly useful if you want to overclock the CPU cores, because it means that the reference clock only affects the CPU cores and none of the other parts inside your CPU. In asynchronous mode, there are 2 distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the CPU PLL, and another provides the 100 MHz reference clock for the SoC PLLs. That means you can increase the reference clock for the CPU cores independent of your CPU's other parts. This may come in handy when fine-tuning using either Precision Boost Overdrive or OC mode. In the Asus ROG BIOS, you can choose the clock generator mode by setting AI Overclock Tuner. If set to auto, then the internal clock generator is used. If set to manual, the external clock generator is used. You can choose synchronous or asynchronous mode for the external clock generator. The CPU core voltage is provided by the VDDCR CPU internal voltage rail, which is powered by the VDDCR external voltage rail. The internal voltage rail is bypassed, thus the external voltage rail controls the core voltage directly. You don't need to adjust this voltage in regular operation with Precision Boost. However, if you want to set a manual overclock in OC mode, you must configure the voltage directly. There are 2 ways to configure the voltage. Configure the OC VID, which sets the VID the CPU will request to the voltage controller, or configure the VDDCR external voltage rail directly, which configures the output voltage of the voltage controller. In practical terms, there's no difference between the 2 approaches. In the Asus ROG BIOS, you can configure the OC VID via the Extreme Tweaker CPU core ratio per CCX submenu. Alternatively, you can manually adjust the OC VID in the AMD Overclocking manual CPU overclocking submenu. In the Asus ROG BIOS, you can configure the VDDCR voltage rail directly in the Extreme Tweaker by adjusting the CPU core voltage setting. The Infinity Fabric, sometimes called the Scalable Data Fabric, is the main communication method for all the chips on the Raphael package to talk to each other. Every chip on the package has a couple of GMI links, which is used to send data from and to the CCDs and the IOD. The Infinity Fabric frequency and performance are most relevant for performance tuning with regards to the memory subsystem performance. Since the DDR5 memory controllers are located on the I/O die, if the CPU cores need to store or retrieve data to and from the DDR5 memory, it has to go via the Infinity Fabric to the I/O die. The fabric frequency, or F-clock, is generated by the SoC PLL, derived from a 100 MHz reference clock input. The reference clock is multiplied by the F-clock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric used to be 1-to-1 with the memory controller and system memory. However, that's different on AMD Raphael. Instead, the Infinity Fabric is decoupled from the system memory and memory controller frequency. By default, it runs at 1733 MHz. It is still suggested that running everything in synchronous mode will provide you with the most optimal performance. And just like on Zen 3, a high enough memory frequency will help you overcome the performance penalty. But given the DDR5 memory frequency and overclocking capabilities, I wouldn't suggest that you pursue running everything in synchronous mode. Just run it asynchronous and that will provide you with plenty of performance. In the Asus ROG BIOS, you can configure the fabric frequency via the F-clock frequency setting in the Extreme Tweaker menu. Alternatively, you can also adjust the frequency in the AMD Overclocking Infinity Fabric Frequency and Dividers submenu. The VDD-G voltage supply, derived via an internal voltage regulator from the VDDCR miscellaneous voltage rail, provides the fabric voltage. There are a total of 4 VDD-G voltage rails available for manual adjustment. Note that the VDD-G voltage does not automatically adjust with the VDDCR miscellaneous voltage rail. So if you need to increase VDD-G, for example, to support higher memory frequency, you need to change it manually. In the Asus ROG BIOS, you can configure the VDDCR miscellaneous voltage rail in the Extreme Tweaker menu. Alternatively, you can adjust the voltage by accessing the AMD Overclocking VDD Miscellaneous 1 submenu. In the Asus ROG BIOS, you can configure the VDD-G voltage by accessing the AMD Overclocking VDD-G voltage control submenu. AMD Raphael CPUs have 2 DDR5 Unified Memory Controllers, or UMCs, embedded in the I/O die. The memory controller should be able to support DDR4, but AMD has made it very clear that from Zen 4 onwards, it's DDR5 all the way. The Unified Memory Controller Frequency, or UClock, is derived from the UMC clock, one of the SoC PLLs. The UMC clock is driven by a 100 MHz reference clock derived from either an internal or external clock generator. The memory controller frequency is tied directly to the system memory frequency. It can run at either the same or half its frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. Still, you can theoretically increase it up to 6000 MHz when running DDR5 12000. In the Asus ROG BIOS, you can configure the memory controller frequency via the memory frequency setting. You can force the memory controller to run at half the memory frequency by accessing the AMD Overclocking Infinity Fabric Frequency and Dividers submenu and setting UClock Div1 mode. The memory controller voltage is provided by the VDDCR SoC voltage rail. You may need to increase the voltage to increase the system memory frequency. This will also increase the voltage for other IP blocks powered by the VDDCR SoC voltage rail, such as the SMU and PSP. In the Asus ROG BIOS, you can configure the VDDCR SoC voltage rail by adjusting the CPU SoC voltage setting. Alternatively, you can change the AMD Overclocking SoC voltage submenu voltage. AMD Raphael is AMD's very first CPU supporting DDR5 memory. And while it may sound like a great technological jump from DDR4 to DDR5, overclocking DDR5 is actually very similar to overclocking DDR4. There are also 2 new features related to memory clocking: EXPO and DDR on the fly. The DDR5 memory frequency, or IMClock, is derived from the UMC clock, one of the SoC PLLs. The UMC clock is driven by a 100 MHz reference clock derived from either an internal or external clock generator. Without adjusting the reference clock, you can set the memory controller frequency between 1000 MHz and 6000 MHz, so all the way up to DDR5 12000. In the Asus ROG BIOS, you can configure the memory frequency via the memory frequency setting. Alternatively, you can set the memory frequency in the AMD Overclocking DDR Timings configuration submenu by adjusting the memory target speed setting. Of course, Raphael also supports overriding some of the memory timings. Here's a full list of the memory timings override that AMD Raphael supports. In the Asus ROG BIOS, you can access the memory timings in the Extreme Tweaker DRAM Timing Control submenu. Alternatively, you can also access the memory timings in the AMD Overclocking DDR SPD timing and DDR non-SPD timing submenus. As we already know, there is a significant difference between DDR4 and DDR5 when it comes to voltage supply. On DDR5, the majority of the memory voltage is handled by the onboard PMIC. PMIC stands for Power Management Integrated Circuit. The DDR5 PMIC has two voltage inputs, 5 volt and 3.3 volt. The specification further defines 4 switching output regulators and 2 LDO outputs of 1.8 volt and 1 volt. The PMIC also has many other features such as I2C and I3C, over voltage and over temperature protection, and so on. Every DDR5 stick has its own PMIC, so you can run different voltages on the sticks. Fortunately, most motherboards will allow you to sync the voltage of your memory modules. There's still one memory-related voltage regulated by the CPU, the VDDP DDR voltage. VDDP is the supply voltage for the DDR5 bus signaling and is derived from the VDDIO MEM voltage rail. By definition, VDDP should always be 100 mV lower than the VDDIO MEM voltage. While it is derived from the VDDIO voltage rail, VDDP does not automatically adjust with the rail. So if you want to change the VDDP, you must manually do so via the BIOS options. Of course, motherboard vendors can implement other rules to facilitate voltage configuration. In the Asus ROG BIOS, you can access the DDR5 memory voltages in the Extreme Tweaker Advanced Memory Voltages submenu. VDDD and VDDQ are also available in the main Extreme Tweaker menu. Alternatively, you can access the DDR5 memory voltages in the AMD VDDIO Voltage Control and VPP Voltage Control submenus. In the Asus ROG BIOS, you can configure the VDDIO MEM and VDDP DDR voltage rails in the Extreme Tweaker submenu. Alternatively, you can adjust the VDDIO MEM voltage in the AMD Overclocking VDDIO Voltage Control submenu under the APU VDDIO Adjust option and the VDDP DDR voltage in the AMD Overclocking VDDP Voltage Control submenu. AMD Extended Profiles for Overclocking, or EXPO in short, is an AMD technology that encourages memory vendors like G.Skill to program higher performance settings onto the memory sticks. Higher performance in this case means higher frequency, better timings, and the appropriate voltages. If your motherboard supports EXPO and your memory sticks have EXPO profiles, that means that you can enable extra performance with the click of a single button in the BIOS. If this sounds very familiar to you, it's because it is. This is not the first time AMD has ventured into high-performance memory specification. In 2012, AMD had AMD Memory Profile, or AMP, for DDR3 memory. Some of you may also remember AMD releasing their own Radeon memory sticks. Initially, the standard was not supposed to be named EXPO, but RAMP. RAMP stood for Ryzen Accelerated Memory Profile. AMD EXPO has 5 main sections. One section for the general EXPO information, 2 sections for 2 EXPO profiles, a section for CRC, and a user profile section. Each EXPO profile has 2 sections, one with mandatory parameters and one with the optional parameters. At the moment of taping, it appears that AMD EXPO is a self-certification program where memory vendors can claim EXPO readiness. The EXPO specification outlines a minimum stability requirement of running memtest and 3DMark for 8 hours. Additionally, a 50-cycle reboot test should be performed to ensure ACPI state transition stability. Since EXPO validation seems to be still quite rudimentary, it is expected that early adopters will face some stability and compatibility issues in the beginning. I'm sure that over time, validation and certification will become a lot better, and I'm also sure that a lot of effort will go into validation work by the motherboard and memory vendors. But it's important to know that as an early adopter, probably you'll have to pay the early adopter tax on this one. In the Asus ROG BIOS, you can enable EXPO in the Extreme Tweaker menu by adjusting the AI Overclock Tuner setting. EXPO 1 will load only the memory primary timings, the memory frequency, and memory voltages. The rest of the profile timings is ignored and tuned by the ASUS motherboard auto rules. EXPO 2 will also load the rest of the complete EXPO profile. A new feature on AMD Ryzen CPUs is the ability to overclock the memory automatically at runtime. This feature is called DDR on the fly mode, and it's available on systems where EXPO is present and enabled. DDR on the fly OC mode is active only when explicitly enabled. When enabled, spare DFP states are used to store different EXPO profiles. At boot, the CPU will train the various memory profiles. That ensures the CPU can dynamically change P state at runtime to change the memory performance. While DDR on the fly OC mode is available in the AMD BIOS, unfortunately I could not get it to work at the time of writing. I can enable the function, but the system will not complete post, resulting in the need to clear CMOS. This function may work on other motherboards, BIOSes, or with different memory, or with future AGESA updates. In the ASUS ROG BIOS, you can enable DDR on the fly OC mode in the AMD Overclocking DDR timing configuration submenu. Navigate to the DDR and Infinity Fabric Frequency Timings submenu, then DDR Options. Then access the DDR Timing Configuration submenu. Here you can enable DDR on the fly. Since it's AMD's first foray with DDR5 memory and DDR5 overclocking, I have no doubt that at the very beginning and at launch, there will be some issues with reaching those really high DDR5 frequencies. In order to increase your chance at a successful memory overclock, I recommend you disable one memory controller option called Memory Context Restore. Memory Context Restore enables or disables forced DRAM retraining at every boot. Training is a DRAM process that aims to optimize the signal integrity between the CPU memory controller and DRAM memory chips. Better signal integrity means better stability at higher frequencies. Memory training can be a lengthy process, so to improve a system's boot up speed, BIOS routines typically skip some parts or even the entire process. I find that disabling this option and thus forcing the DRAM training process on every boot significantly improves memory stability at higher frequencies. Sadly, it also lengthens the boot up process. In the ASUS ROG BIOS, you can disable Memory Context Restore in the Extreme Tweaker DRAM Timing Control submenu. Brand new on AMD Raphael is that there's now integrated graphics on an AMD CPU. While that would technically, I guess, make it an APU, AMD still distinguishes between APU and CPU. There are a couple of crucial differences with the APUs. First, the graphics cores are integrated into the I/O die. That's a separate chip from the CPU core dies. That's different from the APUs, where everything is integrated into a single die. Second, the graphics on Raphael are not meant to run any kind of 3D load. It, of course, can, but it's abysmal performance. Since the integrated graphics are not to be used for any 3D workload, overclocking the integrated graphics is currently not supported, and I don't think support will come in the future.